In this video, I'll introduce the idea of interpolation. After studying this video, you should be able to define interpolation and explain how its goal is different from the goal of curve fitting that we looked at previously. You should be able to implement polynomial interpolation in MATLAB and identify some of the potential problems that can arise in polynomial interpolation. So let's look at a comparison between interpolation and curve fitting. So here we're looking at two data sets. It's the identical data. It's the same 4 data points. Now, we could fit a linear equation through those 4 data points, like so. And remember, we did that. We were minimizing the sum of the squares of those residuals. And overall, conceptually, what we're doing is we're minimizing the error between the mathematical model and the data. In the figure to the right, we're going to interpolate between those 4 data points. And when we interpolate, the difference is we are going to make sure that we use a function, usually a polynomial, that passes through every data point. So you see that polynomial is passing through every single data point rather than minimizing the error of the data point. And that's the principal difference. So numerically, what's happening with curve fitting is we're minimizing the error between the model and the data. Numerically, what's happening with interpolation is we're finding a polynomial that passes exactly through every data point. Okay? And one thing that we'll talk about is if, in this case, we have 4 data points, that means we are going to have a cubic polynomial. And we'll talk more about why in a minute. But first, let's talk about some applications of interpolation. So one application is to calculate intermediate values in a table of very accurate data. So if we know that the data doesn't have uncertainty in it, we're not using a mathematical model to try and correct for that uncertainty or explain that uncertainty. We are just going to take the data as basically being factual and use interpolation to find intermediate values. Some examples of this are thermodynamic property tables that you'll encounter if you take thermodynamics, Engineering 224 at most community colleges. When we get into solving differential equations numerically, the numerical solution is a table of data. And if we want intermediate values in that data, we can use interpolation to find those intermediate values. Another common place where interpolation shows up is in computer graphics, where we want to increase resolution. We might interpolate a graphic onto a finer grid. Interpolation is also used in the development of many other numerical methods algorithms. We'll look at it in Engineering 240 for numerical integration and differential equation, ordinary differential equation solvers. In general, you're going to use interpolation when you know the data is very accurate and you need the intermediate values. Another note is you don't care really about what that mathematical model is that you're using, and we'll generally just use a polynomial. Well, curve fit, when the data has errors or uncertainty, but, and this is important, you have some hypothesis that the system should follow some mathematical model. So we have some physical knowledge about how we expect the system to behave, and we're going to try and fit that mathematical model to the data. So that's the critical difference between curve fitting and interpolation. So now let's look at how we can do polynomial interpolation. So here's that cubic polynomial through 4 data points again. And any n-1th degree polynomial is going to be uniquely defined by n data points. So for example, a line, which is a first degree polynomial, is going to be uniquely defined by 2 data points. A quadratic is a second degree polynomial, and that will be uniquely defined by 3 data points. A cubic is a third degree polynomial, and that will be uniquely defined by 4 data points. And we can see how this is the case by just using this general form of a polynomial equation and successively plugging in the data points to develop a linear system of equations for the polynomial coefficients. So here we have the general form of a polynomial. F of x is equal to some p1 x to the n minus 1 plus p2 x to the n minus 2 onwards to some p to the n. And what I'll do now is look at just plugging in, say, for a cubic polynomial, we would have f at x1, which would be our value at x1, is equal to p1 x1 cubed plus p2 x1 squared plus p3 x1 plus p4. So that gives us a linear equation. So the data points would be x1 and f of x1 would be our data point. And we now have a linear equation, a linear combination of x1 cubed, which is now just a constant, times p1, x1 squared, which is now just a constant, times p2, x1 times p3, and 1 times p4. And we can write this again for f of x2, the next data point, that's equal to p1 x2 cubed plus p2 x2 squared plus p3 x2 plus p4. Similarly, f of x3 is going to be p1 x3 cubed plus p2 x3 squared plus p3 x3 plus p4, and f of x4 is equal to p1 x to the x4 cubed plus p2 x4 squared plus p3 x4 plus p4. And now we have a 4 by 4 linear system to solve for p1, p2, p3, p4. Once we solve for p1, p2, p3, and p4, we can use that to evaluate intermediate points. So again, here's like our 3 points, x1, f of x1, it's right there. Right here would be x2, f of x2, x3, f of x3, and x4, f of x4. So we've used those 4 points to find the equation of the cubic that passes through all 4 points, and now we can use that cubic to say calculate an intermediate value here or an intermediate value there, anywhere within the range of our polynomial. So let's look at how we can do that in MATLAB. It's actually quite easy. Recall that the polyfit function sets up a matrix of basis function evaluations for a general linear least squares curve fit that uses left division. And if we go back here, that's basically what we're doing. We are setting up basis functions. Here would be our z1, z2, z3, and z4 is just equal to 1. So we've set up 4 basis functions and then set up that matrix. But if you recall from the general linear least squares video where we talked about how polyfit works, that system was always overdetermined. Well, if it turns out that if the number of data points is just n plus 1, or 1 more data point than the degree of the polynomial, then it's not an overdetermined system, and it'll be just solved as a regular linear system using left division, and the resulting polynomial will be an interpolation instead of a curve fit. So it's going to be a curve fit. Polyfit is going to be a curve fit if our number of points is greater than n plus 1, where n is the degree of the polynomial. It's going to be interpolation if our number of points is equal to 1 more than the degree of the polynomial. If the number of points is less than the degree of polynomial, then the system is underdetermined and polyfit will return an error. So here's an example using a cubic polynomial to interpolate the value of y corresponding to x equals 2.5. So here's 4 data points, which is what we need for a cubic interpolating polynomial. Then we'll call polyfit with a 3 for the cubic, and then just use the polyval function to estimate the value, to calculate the value at x equals 2.5 using those polynomial coefficients that output from p. And recall from before, those polynomial coefficients are always going to be in that order, p1, p2 to pn, where the p1 is, in this case, the coefficient to x cubed, p2, coefficient to x squared, and so on. Another thing that we'll do sometimes is generate interpolated data. So instead of just finding data at a single value of 2.5, so that was for a single value, maybe we have data for 4 values here, but maybe we want to generate data, say 100 points in between those 4 values. So where we could do that is just set up a vector of x values here, and then again just use polyval to interpolate. We'll use that interpolating polynomial to calculate interpolated data for each of those x values. Again, just plugging those x values into the polynomial that's defined by p. So let's talk about some potential issues with polynomial interpolation. So first, consider the linear system that results from fitting a quadratic through 3 data points. So the system looks like this. And we've talked about this matrix before. This is actually a Vandermonde matrix where, depending on the values of x, we're going to see the columns are going to vary by several, potentially by several orders of magnitude. And this matrix is very ill-conditioned, which means it's vulnerable to round-off error, has a condition number very much larger than 1. And we can try scaling it, but in general, it's a challenging matrix to work with, and the problem gets worse as we go to higher order polynomials. So if we went up to a cubic or a quartic or a 6th or 7th order polynomial, it just exacerbates the problem. And we'll look at 2 alternate interpolation approaches in future videos that can help address this round-off error problem. One is Lagrange polynomials, and there we'll directly solve for the coefficients for the polynomial rather than using a linear system to solve it, so we kind of avoid that round-off error problem that can pop up in solving linear systems. The other will be piecewise interpolation, and those are called splines. And we'll get to both of those in 2 future videos. Let's talk about another potential issue with oscillations. So here is a 10th order polynomial interpolation, and you can see the data, if we follow the data, it kind of goes like this, these data points. And you can see the interpolating polynomial does pretty well, maybe from here to about here. It seems to pretty accurately follow the data. But you see this 10th order polynomial drifts wildly outside the range of the data at these first 2 points and at the last point here. We call these oscillations. And this is not due to round-off error. This is just what happens with the 10th order polynomial as the coefficients are solved to make that polynomial pass through every single one of these data points. The resulting polynomial has these wild swings between the data points. And we know that most likely here between 0 and 0.1, intermediate data should be right in that range. But our interpolating polynomial is telling us that it's up here. So we have very large error in the interpolation. And this problem of oscillations will happen anytime you get into a higher order polynomial, even as low order as 4th or 5th order, depending on the data set that you're looking at. This is another issue that we can address, and we will again address this issue with piecewise interpolation, also called splines. We'll look at that in a future video. The last thing I want to talk about is the hazards of extrapolation. So here's that same 4 data points that we had for the cubic interpolating polynomial earlier in this video. And what I've done here is done an interpolation on the first 3 data points with a quadratic. So the blue line here is a quadratic. And then the red line is the cubic. So the cubic polynomial goes through all 4 points pretty nicely, but the quadratic, what I've done is taken the first 3, and we see it's reasonably close between the first 3 data points, and that's where we would be interpolating, because the quadratic is only defined by those 3 points. To go out to this region with the quadratic, that would be an extrapolation, because we're going outside the range of the data that was used to generate the quadratic interpolating polynomial. And we don't want to do that, and you can see here that we get pretty large errors in how well that extrapolating that quadratic polynomial predicts the data after this last data point. So again, interpolation is going to be useful for finding intermediate values. It needs to be within the range of the known data set. Extrapolation, basically taking the interpolated polynomial, so in this case the quadratic that we generated with these 3 points, taking that interpolated polynomial and using that to extrapolate for values of x greater than 1.6 causes large errors. And it's just, there's no way to correct it. Extrapolation is just dangerous, generally not a good idea. One note, this is in contrast to curve fitting, and in curve fitting, what we were talking about before, it may be reasonable to use a model to predict results outside the range of the data that you use to find the model coefficients. And remember, this is due to that critical difference between interpolation and curve fitting. In curve fitting, we have some mathematical model that we are hypothesizing describes the behavior of the data. And so going outside the range of the data that we use to calculate the coefficients of that model might be fine as long as we have reason to believe that the mathematical model still applies. For interpolation, we're just using a polynomial and whatever polynomial it takes to get the interpolating polynomial to go through every single data point. And so it's only good for finding intermediate values. We don't know what that interpolating polynomial is going to do once it goes outside the range of the data. And in fact, we already saw with oscillations that as we get near the edge of the range of the data, interpolating polynomials can start oscillating wildly. So the bottom line there is just don't extrapolate with an interpolating polynomial. And that concludes this video. We'll look at splines and Lagrange polynomials in a couple videos coming up.